Well, good morning dear and welcome back. So you have started watching video lecture on machine learning. Specifically we are discussing support vector machine. Today we are going to discuss more on advantage of making kernel trick and how to design a kernel. That also I will try to introduce you with that concept. Okay. So just recap. So you have now seen that support vector machine can not only be used for classifying linearly separable problem, but also with some arrangement it can be used for problems which are linearly not separable. Okay. And the idea is, say this is my 2D samples, and surely as you can see that they are not separable in this 2 dimension. So we have transformed the data in a higher dimensional feature space. You see there is another dimension we have, and then we are projecting all the data using that mapping function phi. Okay, we call it mapping function, and now all the data are looking like this, okay, in the higher dimensional feature space. So they are linearly separable, and here we can actually apply support vector machine and it will work same as it would have worked in lower dimensional feature space, provided the samples were linearly separable. So that is the concept of taking the data to higher dimensional feature space. And if you ask question that whether it is always possible to find such a feature space, the answer is yes. Mercer's theorem, using Mercer's theorem, it can be proved that we can design a higher dimensional feature space where the data which are not linearly separable in lower dimensional feature space will be linearly separable. Okay. So that is the idea. So we are using the notation. Sometimes the notations should not confuse you. This is sample I. Also there during training we are using the notation as support vector. Okay. And this is also used many other literature. Xi, they are same, xj, this is sj equal to xj, some other notation, and of course xi equal to x. Also to avoid this kind of notation we represent them in the form of vector, okay, and xj as z. Okay, this is also a vector. So you see in higher dimensional feature space where the data are linearly separable, our Lagrangian multiplier, Lagrangian function will look like this. Okay. So basically earlier they were x, z or whatever xi, xj, but in the higher dimensional feature space x has been transformed or mapped using feature mapping phi, and this is the new identity of the samples, okay, in the higher dimensional feature space. And again there will be dot product between these two, and you know this is vector dot as we have written, but sometimes of course when we will actually do the multiplication, okay, in matrix form, this is x transpose phi z, okay, or the phi z transpose phi x. Okay. So these are things which you know already. Now let us, so this has made our support vector machine capable of handling nonlinear problem also. Okay. So support vector machine is actually original our optimal classifier plus kernel trick. Okay. So, we are trying to discuss the kernel trick here more detail, how you can get benefit out of it will be explained to you. You see, the doing feature mapping and finding a suitable phi is extremely cumbersome. So, kernel trick is to reap the benefit of actually transforming the data to feature space, but do not go to that space literally. You be confined to the lower dimensional feature space and try to extract the same benefit. How we are going to discuss this now. Say you have samples and then phi functions. So, now new sample in higher dimensional feature space. Say how it will look like when I have say two dimensional vector x equals to x1 x2. Okay. So, this is this belongs to the range space n equal to 2, and say that we are trying to design a phi which will take the all pair of monomial terms. Okay. For mapping, say we are we have decided to take that. Okay. So, what are the terms now? All pairwise monomial terms x1 dot x1, x1 dot x2, x2 dot x1, x2 dot x2. So, this becomes 1, 2, 3, 4 dimension. Okay. So, it was originally 2 dimension, it became 4. Now, see if we repeat the same thing, now x is 3 dimensional feature vector in the lower dimension x1, x2, x3, and then how it will be in the higher dimensional feature space if we decide that we will use the pair of monomial terms to project the data. It will be x1 dot x2, x1 x2, x1 x3, x2 x1, x2 x2, x2 x3, x3 x1. So, rhythm you can see x3 x2, x3 x3, and there could be some term which might be same. For example, here they are same, but we are writing them to show you the real dimension which they are taking our sample to. Okay. So, this is 3 dimensional, this is becoming 9 dimensional. Okay. Similarly, phi z also will now belong to 9 dimension. Okay. So, in general we can write that because the feature space becoming n square, there are n square elements. So, you need order of n square time to compute phi x, okay, or in that sense phi x transpose phi z to make that dot product, between these two vectors. Okay. So, you need n square time complexity. Okay. So, time complexity we say in theoretical term it is order of n square. Now, how kernel can reduce this complexity? Now, see, suppose I have decided not to go to the higher dimensional feature space. So, if I do the same dot product in the lower dimensional original feature space, then k kernel function x dot z must be equal to, because the effect I need this, right, it must be equal to that. Okay. And if you now see this is equal to x transpose z square if I do the dot product. Okay. So, this must be equal to this, and what is this? This, when I am performing that dot product is of this nature. You can see x transpose z I equals to 1 to n x I z I, j equals to 1 to n x j z j. So, matrix multiplication. Okay. So, that is why they are multiplication is summation now. So, these are following the matrix multiplication rule. You can see this is of the order of n. So, if I could find such a kernel function which will be equivalent to this, and if I operate in this original domain, then the computational complexity is of the order of n. Okay. when I talk about you see n square, there could be actually n square by 2 because there are many terms which are same, but again the order remains, computation order remains of the order of n square here. If you just really take data to a feature space, and if you do not do that, use a kernel, then the complexity becomes O(n). Okay. So, this is kernel trick. So, if we choose then in more general form, okay, instead of just showing a example, right, and how we can reduce it. The other day we gave an example. You could just do the same thing here. Okay. So, x1, x2 dot z1, z2, okay, equals to phi. That means phi x transpose, and then you can write the phi z also, phi x transpose, say here, okay, and phi z. So, you can calculate that, right, this times this plus, so this time this plus this time this plus this time this. Likewise, you can compute and you can simplify, and then you will see that it will be a cubic kernel. Okay. So, instead of 2, it could be expressed with some algebra, you will be able to do that. Okay. So, this is the feelings of kernel trick, which helps you in reducing the complexity. So, in general form, we write the kernel function, polynomial kernel function, adding a constant c and making the order d, and then you can see what will be phi x. Phi x will be, again, if we are deciding that we will project the data considering all pairs of monomial term here also. Okay. So, here the monomial terms will, d is the dimension. So, it will be of the order of d. Okay, is huge, you see. So, n plus d means n is the dimension of the feature in original domain plus d times d. So, you see, so you can see that all n plus d features of monomial terms up to the order of d, roughly it will be n plus d to the power d features, which is huge. But with this our quadratic kernel, the computation will still be order of n. Okay. So, this is the advantage. Now, how to make your own kernel? You know now what kernel trick is, how kernel trick benefits our computation. Now, how to make your own kernel? Okay. You have only sample and level. Okay. So, from intuition, you see, if you have two class sample, x belongs to I class, j belongs to z belongs to z class, then if they are similar, then the kernel function which you are going to design of your own should be large, and if x and z are dissimilar, then the kernel function will be small. Why? Because you see, we are calculating dot product. Say you have a vector x, and if you have another vector z. So, if the angle between them is small, tending towards 0, okay, then this dot product x and z will be the maximum, is large, it will tend towards 1, isn't it? And on the contrary, if this is my x, this is my z, and the angle theta is tending towards pi by 2, then x and z will tend towards 0. That is very small value. Okay, we in literal sense we are trying to tell you that kernel should have this property, means our two class samples, if they are similar, because I do not know the sample will randomly come. Okay, and if the they are similar classes are similar, then kernel value should be large. If they are small, dissimilar, then kernel value should be small. So, this is a very important criteria which intuitively will help you to design your own kernel. And then there is a concept called kernel matrix, okay, which is nothing but the kernel, each element of the matrix is a kernel function making dot product with the samples. You see, now support vector machine as a linear machine, what we are doing, we are calculating this, okay. You do not need any kernel, anything, okay. So directly samples are there, we are calculating the dot product. Now, support vector machine as a nonlinear machine, then if you try to train using say an algorithm called SMO like algorithm, then you have that the objective function which you need to maximize with respect to Lagrangian multiplier alpha, and then the xz is replaced with the feature mapping function phi xi, phi xz or phi xt, phi z, okay. If you are talking about on the ground computing the dot product between these two samples, right, they are in the higher dimensional feature space. Then how the matrix will look like? Say I have m number of samples, I have m number of samples, actually m point, and these need not be your training samples, okay. They could be for checking your, for designing the kernel, okay. They could be any point, say, and then the we can just think of a matrix, say for m points, x1, x2 up to xm, they need not be the training samples, any point. I am trying to test that I have something in my mind, okay, this will be my kernel. So, whether that kernel is a valid one, I need to see, right. So, we can do check by formulating a matrix like this, phi x1 transpose phi x1, then x1 transpose all other samples up to phi xm. Second row phi x2 transpose phi x1, so with x2 transpose all the other sample. Third row phi x3 transpose and all the other sample transformed in the feature domain, and up to phi xm transpose phi x1 up to phi xm transpose phi xm. So, this will be my m cross n matrix in the feature domain when your samples points have been transformed using the feature mapping function. So, computation of this, as we have seen, is hugely difficult, of the order of n square, and we do not want that. So, we are actually designing a matrix which is called kernel matrix, okay. So, how to make a difference between these two, I do not know, okay. Maybe this is not a kernel matrix, this is a feature mapping matrix, and then I am applying kernel trick, that I am trying to figure out a function which will represent this as this as this, and all, okay. So, all these matrix elements will now be replaced by dot product of my kernel function. These are not kernel function, these are feature mapping function, these are now kernel function. It could be quadratic, it could be linear, it could be anything, right. So, this, and once you formulated this matrix, then if you can show that, okay, this is a symmetric matrix, of course, okay, that means is transpose equals to the same matrix. So, but if you can so that this matrix is symmetric and positive semi-definite. Positive semi-definite means eigenvalues of this matrix, eigenvalues alpha I, eigenvalue lambda, otherwise there will be misconception. Lambda i's will be greater than equal to 0. This is the definition of positive semi-definite. Okay. Positive definite means this. Okay. Positive semi-definite. So, we will prove afterwards that your function kernel function, this kernel function will be a valid kernel provided the kernel matrix which you have constituted using this sample can be proved to be symmetric, positive semi-definite. Okay. And this we will use for nonlinear classifier with kernel trick. Okay. You see. So, we will not use this definitely if you have a problem for solving nonlinearly separable problem. So, what we will do? We will apply trick, we will define a kernel function, and there are kernel function, most common kernel functions are what is called linear kernel function, xt, quadratic kernel function, then you have so the other day I have already shown you that you have a kernel function like so this is called your Gaussian kernel, Gaussian kernel. So, this is very highly used kernel. See, and you see all of them have this characteristic feature that if x and z are very similar, okay, so this will be 0. So, e to the power 0. So, it will tends towards 1, the maximum value. So, the value maximum to minimum will actually it will be between 0 and 1, because if they are very dissimilar, then this will be a large quantity. Okay, e to the power minus large quantity will tends towards 0. So, it is the can it be qualified to be a kernel? Yes, because it is lying between 0 and 1, and when it is similar then it is large, when dissimilar it is small. So, all these kernel have the similar characteristic feature. Okay. So, that gives you an hands-on that how kernel can be designed. So, if you have samples and you have some kernel in your mind, then you can do research that kernel trick you are applying and whether this matrix is positive semi-definite, whether the matrix is symmetric, and if they are, then whether each element is actually representing can represent this type of mapping. If they are, then it can be a valid kernel. So, people have done over the years lot of research, and many ready-made kernel function actually are available for your use. And those kernel functions, since they are based on trick, what is the trick? That is what I told, that if you use that kernel function and apply to your samples for training, then you will the training and testing, then it will have the same effect of actually taking those samples, spending lot of computation time to a higher dimensional feature space, okay, and then doing classification. So, using kernel trick, we can always use support vector machine as a linear classifier in a very higher dimensional feature space. And once training is there in higher dimensional feature space, we can also test or validate our kernel, and for prediction also we can use wherever sample, whenever sample will be coming to you for prediction, using same kernel function you transfer that sample to a higher dimensional feature space where the classification has been done using linear classification principle, then support vector will tell that which class it belongs. Okay. So, even you may not need to come back to the original domain, so this is a wonderful kernel trick, and of course, this kind of matrix, when the elements are dot product, called also gram matrix. So, this is very important to know. You should not have any confusion between kernel function and kernel matrix. Okay. And we will talk more about this in the next class. Till then, stay safe. Goodbye.